So thank you very much for invitation. First of all, I'd like to thank the organizers, Luca and Aria, for their efforts in organizing this workshop on axion. Today I will talk about a trapping effect on the axion. And I have worked on the various scenarios where the axion is trapped in the Wong vacuum. And today's talk is based on these papers. And in the first one, we considered the temperature-dependent trapping potential. And in the second paper, we considered constant peak breaking term. And this is the main subject of this talk. And actually, this is a generalization of our previous work that appeared in 2016. And if I have time, I briefly go through this work where the axion mass arises from first-order phase transition. Okay, so let me begin with introduction. So I briefly go through the strong CP problem so that the other speakers can save their time. And strong CP problem is, of course, the problem why theta parameter appearing in front of this gluon dual operator is so small. And in order to satisfy the neutron EDM bound, theta parameter must be less than about 10 to minus 10. And why theta is so small is a strong CP problem. And one of the plausible solutions is the Peccei-Quinn mechanism, which effectively promotes a theta parameter to a field, namely the axion field, here denoted by A, F is the decay constant. So this combination appearing in the parenthesis should be regarded as an effective theta parameter. And what is interesting is that axion, QCD axion A, acquires potential from this interaction to gluons, and the potential is given by this. And the coefficient chi of T is topological susceptibility, which depends on temperature. So because QCD is asymptotically free, this chi of T is suppressed at high temperatures, but as temperature decreases, it grows and becomes constant at temperature lower than about 150 MeV or so. So the potential looks like this. At high temperatures, the axion potential almost vanishes, so that axion is massless. But as temperature becomes lower than the QCD scale, the potential grows and it becomes constant. Okay, and the potential height is of order 100 MeV to the fourth power. And at a certain point, the QCD axion acquires mass and starts to oscillate about potential minimum, where the CP phase is vanishing small. Okay, so this is how the strong CP problem is solved by the Peccei-Quinn mechanism. And for this mechanism to work, the Peccei-Quinn symmetry must be of very high quality. And because if CP is violated by a large amount, if you add additional peak breaking term, it will shift the potential minimum so that the strong CP phase becomes non-zero, and which becomes inconsistent with observations. For instance, if you introduce higher order terms like this, here capital phi is a PQ scalar field where the QCD axion resides in its phase and its power, then assuming the order 1 CP violation, the n must be greater than 12 or so to satisfy the neutron EDM bound. So any lower dimension operators must be forbidden by a certain symmetry or so. So the PQ symmetry must be of very high quality. So you might think that the adding such an extra PQ breaking term does effective nothing to the QCD axion dynamics because it must be very small. However, this is not necessarily the case because the potential coming from QCD becomes very much suppressed at high temperatures. So even tiny PQ breaking term could dominate the axion potential and might affect the axion dynamics and the abundance. And that is what we studied in a series of papers. And here I focus on the constant additional PQ breaking term and study its effect on the abundance of the QC axion and also fluctuations. And we find that the axion abundance is either enhanced or reduced depending on the initial condition. And in particular, what is interesting is that if the axion is deeply trapped in the Wong vacuum, then the resultant axion abundance becomes independent of decay constant Fa and the initial angle of the axial field. So it means that you can explain all dark matter by the axion by using the trapping effect for any values of Fa. So for instance, even if Fa is as low as the lower bound coming from the stellar cooling argument, you can still explain all dark matter if one uses the trapping effect. Okay, so let me continue with this the review on the conventional scenario. The axion follows this the equation motion in the homogeneous universe, and at a certain point it starts oscillate because potential grows, and at a certain point the last term V prime QCD A becomes comparable to the second term, the Hubble friction force. Then afterwards axion oscillates about the CP conserving minimum. By the way, in this talk I focused on the pre-inflation scenario where the peak symmetry is already broken during inflation, so that axion exists and acquires quantum fluctuation over the Hubble parameter as the inflaton does. And this fluctuation results in the isocurvature perturbation because axion starts oscillate with a slightly different amplitude from point to point in space. Okay. And in the case of QCD axion, because potential height is fixed by the QCD scale, so the mass and decay constant are related to each other, and the axion abundance can be expressed as a function of decay constant Fa, and this finding power comes from the temperature dependence of the potential, and the theta initial is the initial angle defined by this, and the capital F of theta is the anharmonic effect, which becomes larger than unity as initial angle approaches pi. Okay. And from this equation, you can see that for Fa around 10 to 12 GeV, you can explain all dark matter for initial angle over the unity. And this argument sets the upper bound of the so-called classical axion window here. And by the way, lower bound on Fa comes from the stellar cooling argument, such as neutron stars and also neutron burst duration of the supernova 1987A. So I borrowed a very nice figure made by Kieran O'Hare. Probably he's in the audience now. And now everybody uses his figure because it looks so nice. And this figure is showing the axion photon coupling and as a function of axion mass. And this yellow vertical band represents the mass region where you can explain all dark matter by this conventional misalignment mechanism for the initial angle over the unity. But as you can see here, there are many axion search experiments lighter or heavier than micro EV. So the question is, how can we generate the right amount of dark matter in these regions? So for axion mass lighter than micro EV, the axion abundance is too large to explain the dark matter abundance. So you have to suppress the axion abundance somehow. One way is to fine-tune the initial angle much smaller than unity. And for instance, for Fa around 10 to 16 GeV, theta initial must be over 10 to minus 3 or so. And there is some dynamical mechanism to explain such a small initial angle, and as studied in these papers. On the other hand, for the axion mass greater than micro EV, you have to enhance the axion abundance because axion amplitude is too small in this case. And one way is to put the initial position of the axion close to the top of the potential, namely theta initial close to pi. Then here V prime is small so that the onset of oscillation is delayed. So this can be understood by looking at the equation motion. But in this limit, the axion abundance actually becomes very, very sensitive to the initial position of the axion. So it implies that isocurvature perturbation is significantly enhanced in this limit. And I borrowed this figure from my old paper. And so there's a tight upper bound on the Hubble parameter during inflation. And here you have to be below this green line if the axion explains all dark matter. And for Fa around 10 to 12 GeV or so, the Hubble parameter during inflation must be lower than 10 to 7 or 10 to 8 GeV. So this is a usual isocurvature bound. But as you go to small values of FA, the ice curvature bound becomes very, very tight. And this is due to the anharmonic effect I mentioned earlier. So here the final axion abundance becomes very sensitive to the initial position, so that the ice curvature is enhanced, and it means upper bound and upper parameter during inflation becomes very tight in this limit. Also, you can also consider the decays of topological defects, the domain was the cosmic strings, and we will hear more about it in the talk by Kenichi during this workshop. So let me go on to the experimental limits on the explicit peak breaking. Here we consider the constant peak breaking term given by this equation. Here lambda h represents the potential height, and the theta h is the relative phase of this peak breaking term with respect to the potential coming from QCD, and is some integer number. It's domain number of this interaction. And for convenience, let us define the normalized height of the potential, denoted by R, defined by lambda h divided by 100 MeV. Okay, so the potential looks like this. So this gray dashed line represents the potential coming from QCD. So this is the usual potential, and here we added this red dashed line and name this PQ breaking term. Of course, for illustration purpose, the size of peak breaking term is exaggerated. But anyway, the total potential is sum of this gray line and red line, and it is shown by this blue line. So for this case, you can see that there appears a force vacuum here and there. Okay. So this figure shows the bound coming from the neutron EDM on the plane of the relative height of the peak breaking term and the relative phase, theta h, and this gray region are excluded by the neutron EDM bound. And this white region is on the other hand allowed. Okay. So by the way, I set n equals 3 just for simplicity. And for something interesting to happen, the size of peak breaking term must be sufficiently large, because otherwise the axion start to oscillate due to the potential coming from QCD, so nothing happens. But if the peak breaking term is relatively large, the axion first starts to oscillate due to this peak breaking term, and this happens if you are above the horizontal line for each value of FA. So if FA equal to 10 to 10th GeV, and if you are above this blue line, the axion first starts to oscillate due to the peak breaking term. Okay, so then the axion dynamics is significantly modified compared to the conventional scenario. So let us study the axion abundance in this case. So as I mentioned, we assume that the axion starts to oscillate due to the peak breaking term, so that the oscillation, the temperature at the onset of oscillation is higher than that in the conventional scenario. In this case, the subsequent axion dynamics can be broadly classified into the two types. One is what we call smooth transition regime, where the initial position is relatively close to the true minimum, so that the axion first starts to oscillate about minimum close to the origin, so that as temperature grows, the minimum shifts to the CP conserved minimum continuously. On the other hand, for slightly larger initial position, the axion first starts to oscillate about this force vacuum, which is separated from the true vacuum by the potential barrier. So, and the axion is trapped in this force vacuum until the potential coming from QCD grows and the force vacuum disappears. And we call this regime as trapped regime. Let us consider the dynamics in each case. First, in the case of smooth transition regime, the axion starts to oscillate about this minimum, which is given by theta h, and so the axion oscillation is induced, but as temperature grows, the potential coming from QCD comes to dominate, and gradually potential minimum approaches the origin here, where CP is conserved. But the typical time scale for this transition is much slower than the time scale for oscillations. So no particle production takes place in this process. And this mechanism is called adiabatic suppression mechanism, which was extensively studied in the context of cosmological moduli problem. And the axion abundance is determined by the axion oscillation energy when the axion starts to oscillate due to peaky breaking term. And because the onset of oscillation is earlier than usual due to the subsequent cosmic expansion, the final abundance is suppressed compared to the conventional scenario. Okay. In the trapped regime, on the other hand, the axion starts to oscillate about the forced vacuum here and gets trapped for a certain time. And the axion starts to oscillate again when the forced vacuum disappears. And in this case, the temperature at the onset of oscillation, this is second oscillation, is simply determined by the potential height of the peaky breaking term. And as a result, the axion density is given by a function of the axion, the function of the height of the peaky breaking term. Okay. So as you can see here, it is independent of the axion decay constant Fa and the initial angle. So you can explain all dark matter for arbitrary values of Fa as long as the axion is deeply trapped in the forced vacuum. By the way, this fact was first pointed out in this paper. And we numerically calculated axion abundance in the more recent paper. And here I show the axion abundance as a function of the initial angle, theta initial. For theta initial relatively small, close to the origin, the axion first starts to oscillate a minimum close to the CP conserving minimum. So the axion abundance gets suppressed in this regime. And you can see here the axion abundance depends on Fa. In this case, as Fa grows, the axion abundance also becomes larger. But as you can see here, so this triangle corresponds to Fa equal to 10 to the 13th GeV. And here you can explain axion, you can explain all dark matter. In this case, for relatively large value of Fa, this is because the axion abundance is suppressed in the smooth transition regime. On the other hand, in the trapped regime, you can see here the axion abundance is almost the same, independent of the value of Fa. So this is 10 to 14th GeV, and this one corresponds to Fa equal to 10 to 15th GeV. This one is a bit, in this case, the trapping effect is relatively weak, so that it is not, you can see mild dependence on Fa, but otherwise, for all the values of Fa below 10 to 14th GeV, the axion abundance is the same, and also it doesn't depend on the initial angle. This is what I explained on the previous slide, but we confirmed it numerically. But this feature is very nice, but for this choice of parameters, the final axion abundance is a bit too large. So I reduced the value of the R, namely I reduced the potential height of the peaky breaking term. Then I got this figure. So in the trapped regime, you can see the mild dependence on Fa, but for Fa lower than 10 to 11 GeV, the axion abundance is still degenerate, independent of Fa and the initial angle. Okay. So this figure also shows the contour of the axion abundance on the plane of the potential height and the relative phase, theta h. And this is for the smooth transition regime. And in the region below this horizontal line, so nothing happens because the size of peaky breaking is too small to affect it, to affect the axion dynamics. But for the R greater than this horizontal line, the axion abundance is reduced due to the early onset of oscillations. So you can see that axion abundance is reduced. And you can see that you can explain all dark matter for Fa equal to 10 to the 13th GeV in this case, but the relative phase must be suppressed, must be fine-tuned by about 10 to the -10. So this scenario is interesting, but not particularly appealing from a theoretical point of view. But this trapped regime is more interesting. And this left panel is for Fa equal to 10 to 11th GeV, the right panel for 10 to 10th GeV. And again, as you increase the size of the peaky breaking, the axion abundance is modified. But in this case, we are considering trapped regime, so the axion abundance increases as we increase R like this. So this is also the case for F equal to 10 GeV. But what is interesting is that this contour of axion density is almost the same between these figures, left and right panels, even if FAs are quite different. So this is, you can expect all dark matter on the red line, by the way, and the position of these lines coincide with each other. And this is due to the fact that axion abundance is independent of FA in the deep trapped regime. So in the rest of my time, I briefly mentioned isocurvature perturbation. As I mentioned earlier, in the pre-inflation scenario, the axion acquires quantum fluctuations, which induces the isocurvature perturbation, and it can be evaluated by this standard formula, and it must be very small, like the power spectrum isocurvature perturbation must be less than about 8 times 10 to the minus 11. And in the smooth transition regime, the axion abundance is reduced so that in order to explain all dark matter by the QCD axion, the FA must be a bit larger than the conventional scenario. So FA is larger, the isocurvature perturbation is suppressed in this case. In the trapped regime, the effect is more significant because the axion abundance becomes independent of the initial angle as long as axion gets trapped in the force vacuum. So the isocurvature perturbation is significantly suppressed in the trapped regime. And this is the numerical result of the isocurvature perturbation. And this is for the smooth transition regime. And these dots are numerical results, and these lines correspond to the analytic expressions for each case. And this purple dashed line corresponds to the conventional scenario. So this is basically what I showed in the introduction. You have to be below this line. But this isocurvature bound is relaxed to blue line, for instance. And you can see that isocurvature perturbation is relaxed by some factor. Okay. By the way, the isocurvature bound becomes tight for lower value of FAs due to the unharmonic effect. So this is more interesting, I think, and this is for the trapped regime where the axion is trapped in the force vacuum for a long time, so that axion abundance is independent of the initial angle, and the isocurvature perturbation is greatly suppressed. And so this purple line is again the conventional bound, and this dots, the circles, diamonds, and the red dots correspond to numerical results for different values of initial angle. Although there are some scatter among different choices of the initial angle, but you can see that isocurvature bound is relaxed by many orders of magnitude in this case. Okay, so this is a final slide before the conclusion. The reason why the axion abundance is enhanced in the trapped misalignment mechanism is that onset of oscillation is delayed. Okay, and this delay of the onset of oscillation can be also realized if the mass of axion, here axion-like particle, is generated by the first order phase transition. Then because mass appears at a later time, the onset of oscillation is of course delayed, and which enhances the axion abundance. So this is figure again for the axion photon coupling as a function of the axion mass. This red line corresponds to the conventional misaligned mechanism, where the axion abundance is proportional to square root of axion mass. On the other hand, this green line corresponds to the axion abundance, where the axion mass arises from the first order phase transition. In this case, the axion abundance is linear in the axion mass. So you can see that the viable parameter space where axion-like particle explains dark matter is broadened by considering this kind of scenario. So let me wrap up my talk. We considered the effect of PQ breaking term on the dynamics of QCD axion, and we numerically evaluated axion abundance and its isocurvature perturbations. And we found that axion abundance can either enhance or reduce depending on the initial position. And in particular, if the axion is trapped in the Wong vacuum, the axion abundance is enhanced and it becomes independent of FA. Okay? So as a result, the axiom, okay. As a result, axial curvature pathways relax, and I briefly mentioned similar possibility for the axion-like particle. Okay, that's it. Thank you very much for your attention.
Thanks a lot. Very interesting. And let's see if there's any question. Anyone can raise hand now. If not, I have a question, which is, oh, sorry, there is a question from Wen-Yuan. Sure.
Yeah, so I have a question. So in the trapped region, in principle, because you have a force vacuum, then in principle you have bubble negation. I was wondering what is the lifetime of the force vacuum and whether it's put some constraints on this model.
Sorry, due to the internet connection, probably I cannot hear your question well. So can you repeat it again? I'm very sorry.
Oh yeah, no problem. So I mean, so in the trapped region, you have a force vacuum, right? And in principle, because you have a force vacuum, then you can have bubble negation. I was wondering what is the lifetime? I mean, so did you
okay.
actually, yeah.
In this case, actually, in principle, yes, as you said, in principle, the axion can tunnel to the true vacuum through the bubble nucleation. That's possible in principle. However, the potential we consider is very flat, and the typical scale for the axion field is determined by decay constant, which is much larger than the axion mass. So if we calculate the bounce solution, its lifetime is very long, and practically it doesn't happen.
Okay, I see. Thanks.
Thank you for asking.
I had the same question, so thanks, Wen-Yuan. Okay, there's a question from Miguel.
Yes, thanks for the nice talk. So could you explain again how the isocurvature bound is relaxed? This I miss.
Yes. So the point is that axion abundance is independent of the initial angle in the trapped regime. So if this is the case, as you can see here, this is the power spectrum of isocurvature perturbation, and it contains derivative of the axion abundance with respect to the initial angle, because it is initial angle theta initial that fluctuates due to the quantum fluctuations. But in the trapped regime, axion abundance is almost insensitive to the initial angle, because the oscillation energy the axion acquires is simply determined by the timing and potential height when the axion starts to oscillate about potential minimum. And the initial angle here, even if initial angle fluctuates, once the axion gets trapped in the Wong vacuum, it almost forgets where it initially is. So, and axion abundance is simply determined by potential height of the peak breaking interval. And this is the reason why the isocurvature perturbation is suppressed.
Thank you.